So this is starting chapter 15, which is looking at equilibrium reactions. So we've mentioned equilibrium in the previous chapter because we did have it in a reaction that would get essentially rid of an intermediate in a mechanism. So going back over that, an equilibrium is the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, and so two other things to talk about. One is it's a closed system, so that means nothing else is going to come into that equilibrium. And we are going to assume that there's no change in temperature, okay? Just to keep everything kind of the same across everything that we're talking about. So what you're going to see in my notes and on my worksheets are arrows indicating that you have an equilibrium reaction. So this is a more sophisticated arrow, half arrow pointing left, half arrow pointing right. You might see a double-headed arrow in some of my worksheets and other things. I haven't completely converted over to Google. So this is showing you that you have a reversible reaction. So if we take that first equation, I just wrote it over here because I'm going to write some stuff down. If I was given a certain quantity of my reactants, okay, so let's say I was given 0.4 moles of the SO2 and 0.3 moles of the O2. We could assume at the beginning of these reactions that we have none of the other, whether it's the reactant or the products. If they are reversible, you could actually start on either part of this equilibrium. So SO2 and O2, we break the bonds and form SO3. So this side is going down by its stoichiometry. So this goes down by -2x, this goes down by x, and this goes up by 2x. So what we're going to focus on is then at equilibrium, okay, what are the concentrations or what are the number of moles at that point? So I probably showed this to you before. What we're going to talk about is an ice table. And what we're going to do is take a look at, well, how do these reactants and products change as equilibrium is established? So what exactly does equilibrium look like in a graph form? So draw yourself just a very simple XY axis here. And down on your X, write reaction progress, or again, write down time, okay? And then over here on the left, write down molarity, okay? Now, these graphs are always going to be done in molarity. So up here in my example, I did things in moles. So please note that you're going to have to be given the volume of the container in order for you to do what we call concentration calculations. So let's say that this is all done in a 1 liter container, excuse me, and realize that this equilibrium, we must always think of it as in the same container. So I'm going to mark up my axis here, and again, it's not going to be perfect, but I am starting at like a concentration of 0.4 for my SO2, and I'm starting at about 0.3 for my O2. And my SO3 is starting down here on the 0 part because, again, I have none of it to start with. So what an equilibrium graph does is kind of show you what happens to everything and when is equilibrium established. So the SO2, of course, is going to decrease and then level off. O2 also decreases and levels off. And then the SO3 is going to increase and then level off. So we're going to work on the calculations here in a moment, okay? That's not really what I want you to focus on here. Instead, I want you to focus on the graph. So at what point on this graph do you think we've reached equilibrium? Well, equilibrium is reached once everything has established a constant, and that is going to continue on for the rest of that reaction. So once this has reached equilibrium, okay, so I kind of drew a line there, it's not perfect, but once these concentrations have been reached, they're going to continue on for the rest of that reaction. So you're not going to see any change. Now we'll talk about how we could change it, but for right now, what I want you to understand is once it levels off, that's the point of equilibrium. So let's look at the second example, the making of ammonia. So I'm going to make up some data here, and I'm going to do it in molarity just to make it make more sense for the graph. So let's say nitrogen, I'm starting at 0.6, and hydrogen, I'm starting at 0.4. What takes place is this goes down by x, and this goes down by 3x, and this goes up by 2x. So let's say it went down to 0.5 molar for the nitrogen, so the x must be 0.1. And again, we're going to focus on the calculations here in a second. I just want it to be proportional so you can kind of see what I'm doing here. So again, this is minus 3x. So again, you got 3 times the amount of hydrogen as you do the nitrogen. So here are my numbers. Again, we will do the calculations here in a moment, okay? But again, what would the actual graph look like? Again, the graph must be in molarities. There's a couple things that I want you to focus on when you are doing the graph. First off, when you're setting up your axes here, again, don't worry if it's not all that proportional or spread out very nicely. So nitrogen is starting at 0.6, so please label that. Hydrogen is starting at 0.4, and then my ammonia is starting down here at 0. So the ammonia ends up at 0.2, okay? So I'd like you to label it as 0.2 molarity over here on the right. Hydrogen goes all the way down to 0.1. And then the nitrogen ends up at 0.5. So one of my, when I ask you to draw these on quizzes or tests, I do want you to label on the right-hand side exactly what the concentrations are for each one of these, because again, we're just freehanding these. And so I just want to make sure that I know where you got those numbers from, or do you understand that those numbers are, once equilibrium has been established, those are going to be the concentrations. So what I've been doing is essentially an ice chart, okay? So ice charts are very useful for equilibrium concentrations because it's an easy way to kind of organize information in terms of the reactants and the products in an equilibrium. So if I have a reaction of 0.2 moles of hydrogen, 0.2 moles of chlorine, what is the amount of moles if there are 0.12 moles of HCl at equilibrium? So I have 0.2 of this and 0.2 of this, and that just happens to be what it is. So initially, that's going to be my ICE chart, okay, initial change in equilibrium. So I have this going down by x, this goes down by x, this goes up by plus 2x. But what's interesting about some of the problems you're going to see is I'm going to give you something at equilibrium, which is the HCl. So that's going to be 0.12 moles. For this. Now this is 2x, so that must mean x is equal to 0.06 moles. So once I know that, I could subtract that from 0.2, and I get 0.14 moles for my H2 and my Cl2, or my Cl, yeah, Cl2. Please note, it just so happens that they end up to be the same. That is not traditionally always going to be that way. So let's assume that this is in a 1 liter container again. For these ice charts, you can always do them in moles, or you could do them in molarity. So I'll show you the next example in molarity. But let's first graph it, okay? So again, I have 0.1, I got a 0.2. So the H2 and the Cl2 are both starting up at 0.2, and I got nothing down here. Again, this is time, this is molarity. So this goes down to about 0.14, excuse me, and then this goes up to 0.12. And again, it doesn't have to be proportional in terms of you know, the distance between these two, but if that's the 0.14, I want it above the 0.12. So in this last example that I want to finish up with this video is I have this reaction taking place in a 2.5 liter container with a 0.6 moles of methane to start with. At equilibrium, I have 0.078 moles of ethine are present. What are the concentrations at equilibrium? So I'm going to pause the video and then you're going to see the answers here. So this one, I want to do the table with molarity. So what you will see over here on the side is I calculate the molarity of the methane, the CH4, taking the moles divided by the liters, and then this is the ethine, the C2H2, over here on the right-hand side. So if I have 0.24 molarity of the methane, this is starting at 0, 0, minus 2x, this is an x, this is a plus 3x. So if this is my concentration at equilibrium, which I calculated over here, so x must be 0.031. That's what x has to equal. So 3 times that is 0.093 molarity. And then if I subtract twice that minus the 0.24, and again, there's some rounding issues with this, I get 0.18 molarity. So again, the graph down here kind of sloppy, but what you want to show is the H2 and the C2H2 are starting at 0 and going up to their concentrations. And as you can see, even how I drew it, I'm way above where I have my 0.1, and this is not really where everything lines up. But as long as you indicate what the final concentration, or excuse me, the equilibrium concentration for each one of the species, that's going to be fine with me. And again, molarity, and then you're going to have time on the x-axis.